Okay, so in the last class, I introduced the soft SVM algorithm and another way of defining the soft SVM algorithm. In the first case, we saw soft SVM as trying to solve a constrained optimization problem. But then we also saw that this is equivalent to an empirical risk minimization, but with the hinge loss and with a regularizer, a quadratic regularizer. All right. And the advantage of this variant of soft SVM is, one, it has an interpretation in terms of an empirical risk minimization problem, and therefore it can also be used to derive generalization error bounds. But also the other advantage is that you can now design gradient descent or stochastic gradient descent type of algorithms to actually do this minimization more efficiently. All right. The fundamental problem of trying to solve this, either of these variants of soft SVM exactly, is that the complexity of finding the solution scales at least linearly with the dimension of the space and the number of data points, because here the number of constraints is equal to the number of data points. So if you have a very large data set, then it means that the computational complexity also scales at least linearly in that size. So then what do? The solution is to use these approximate gradient descent type of algorithms, specifically stochastic gradient descent. And that's what we'll see in some detail today. And in the last class, we did a very quick analysis of gradient descent, particularly the rate of convergence of gradient descent. We saw that if we choose the step size properly, in particular if the step size is chosen to be b by rho times square root of t, where t is the total number of steps for which you run gradient descent, b is a bound on the norm of x, and or a norm on the distance from where distance between the initial point and the solution, and rho is a bound on the norm of the gradient at any particular point, or equivalently if f is rho Lipschitz, then at the end of t steps, the error is going to be at most b times rho divided by square root of t. All right, and this also holds true even if you replace the gradient with a subgradient, or even if you use stochastic gradient descent, where the stochastic gradient is any vector, any random vector, such that whose expectation lies in the subdifferential set. All right, and essentially the same kind of bounds hold true even if you run stochastic gradient descent, except that all of the guarantees hold only in an expected sense. All right, so this is all of this was gradient descent and stochastic gradient descent for a general minimization problem. Of course, the underlying assumption is that the objective function is convex. Okay, but stochastic gradient descent can particularly be used for empirical risk minimization. But here again, we need the loss function to be convex. All right, so we'll start with some assumptions. So firstly, we'll assume that our hypothesis class contains a bunch of functions which are parameterized by some vector. So for example, if it's a linear net, if it's a, let's say, a neural network, then W is maybe the set of all weights and biases in vectorized form. If you're dealing with linear regression, then W is again the set of all weights and biases, and so on and so forth. Or if, let's say, you're doing polynomial classification, then maybe W consists of all of the coefficients of the polynomial. All right. So just so that we can, so the fundamental assumption is that these free parameters that we have belong to some d-dimensional Euclidean space. That's what we need. And we'll also require the loss function. All right. So HW of X is the prediction made by the class, by the predictor HW. And for now, I don't really require this to be a binary classification problem. It could be any learning problem where the loss function as a function of W is convex. So for every x comma y, the loss function should be a convex function of W. Okay. So the empirical risk minimization basically corresponds to minimizing the following function. I'll now denote the empirical risk as a function of W rather than H because they're equivalent. If L is a convex function of W, then a sum of convex functions is also convex. So therefore, the empirical risk is also a convex function of W. So this automatically means that all of the previous results that we derived, rate of convergence of gradient descent for convex functions, also holds true for gradient descent in trying to solve this empirical risk minimization problem, which is good. All right. So all of that is great. So which means that if you have a convex loss function, then you can do empirical risk minimization just using gradient descent. This is a nice procedure to use. The only problem is that this gradient descent requires you to compute n gradients in every round. Why is that the case? If you take the gradient of Rs of W, remember here that you're taking the gradient with respect to W, this is equal to 1 over n summation I equal to 1 to n gradient L of HW of Xi yi. So the gradient of the empirical risk is a sum of the gradients of the loss functions evaluated for different data points. Right? So these different individual loss functions are going to look quite similar, but nevertheless it still requires you to compute n different gradients. So
Convex function means there is only one minimum, right?
there is unique minimum, yes.
There is only one minimum.
Correct.
Summation of two convex minimums could lead to two minimum, right?
It doesn't.
It doesn't.
It doesn't.
There will be two different places where you can have.
That doesn't happen.
So the convex function here is like y-axis will be plotting L of these things, and x-axis will be varying the xi.
No, here you're varying W, right? The variable that you're optimizing over is W. So you have two loss functions, L of HW of x1 comma y1, and the other function would be L of HW of x2 comma y2. and you're taking the sum of these two.
So for each xi, there will be different convex.
For each xi, corresponding to each xi, this term is convex, right? So there is one function corresponding to each data point. This is a function, this is to be viewed as a function of w, all of the free parameters in your predictor. And the empirical risk is a sum of these, or an average of these convex functions. And a fundamental result in convex analysis says that sums of convex functions are also going to be convex. All right. Okay. So this requires you to compute, for the empirical risk, to compute the gradient, you have to compute n different gradients. So the complexity is order n. Here I'm not really worrying about the complexity in terms of dimensionality. We are assuming that the number of data points is much more than the dimensions involved. Otherwise, the complexity of the dimensions automatically dominate. All right. So is there a way of reducing the complexity? And yes, there is. You can just do stochastic gradient descent. So one way of choosing a gradient is to choose g of w. So you pick a random variable I, which is uniformly distributed over 1, 2, 3 up to n. All right, and the stochastic gradient is going to be the gradient of L of HW computed only for the ith data point. All right. So essentially you pick one data point uniformly at random and then compute the gradient of L with respect to this particular data point. Now this is a stochastic gradient. Why? What is expectation of g of w? I is picked uniformly at random, therefore the expectation is sum over all I. The probability of choosing a particular I is 1 by n, and the random variable in question is L of HW of xi, comma yi. So expectation of g of w is equal to the true gradient of the empirical risk. Therefore, this is a valid stochastic gradient. Okay. So, but in this case, the complexity is essentially just order 1, because you just need to compute one gradient. It's a little more subtle because you still need to be able to pick an I uniformly at random, but that process is a lot simpler to do. That's a lot computationally less intensive to do than computing n gradients. All right. So this is stochastic gradient descent, and now if I do this, then I also inherit the same rate of convergence properties as gradient descent. All right. And similarly, I can derive a rate of convergence bound for empirical risk minimization using stochastic gradient descent. Now, in practice, you do a variant of stochastic gradient descent. So basically, in stochastic gradient descent, you use the stochastic gradient in place of the true gradient. Now, are all kinds of stochastic gradients equivalent? Not really. The analysis of stochastic gradient descent didn't really depend on how you chose the stochastic gradient. Right? It's not a unique way, because for a given function, let's assume that it is smooth, the gradient is unique. But the stochastic gradient is any random function whose expectation is equal to the true gradient. Right? Now, if I give you two different stochastic gradients, they need not be the same. For example, if one of the stochastic gradients has a much higher variance than the other stochastic gradient, then maybe that's worse. Because although in expectation you would be doing well, at times you can go way off, right? Because the only guarantees that you get on the convergence or correctness of stochastic gradient descent is in expectation. So on average you will be doing well. But if at each point you're fluctuating wildly, because after all you're taking random steps, then that's bad. So in that sense, stochastic gradient descent can be improved using what is called batch stochastic gradient descent. And that's just a way of reducing the variance of this SGD step. Right. So instead of picking one data point uniformly at random, you choose a batch of data points uniformly at random. So you pick B points uniformly at random. And set G of W to be 1 over B summation I equal to 1 to B, or say K equal to 1 to B, gradient of L of HW of X IK Y IK. Right, where I1, I2, I3 up to IB are the B data points that are chosen at random. So if you increase the batch size, then the variance of the stochastic gradient becomes lower, okay, because it's a better approximation of the true gradient than standard stochastic gradient descent. But the flip side is that the computational complexity also increases proportional to the batch size. Yeah? Yeah, it's again O of B. All right. So this is nice, and this is something which is generic and can be used for any learning problem, as long as the objective function is convex. In practice, you don't have this property of convexity, but still that's okay if the function is smooth. If the loss function is smooth, then in principle you can still use stochastic gradient descent or batch stochastic gradient descent, and it will still work, except that you'll probably just be converging to a local minimum rather than the global minimum.
Overall complexity is same, right? Because there you do 1 point at a time, stochastic gradient. You do computation 1 point at a time.
Correct.
But here we are doing per batch. But
Correct.
over the whole data, I think it will be same computation.
The point is you don't run over the whole data. That's the whole objective, right? Because remember, it's an iterative process, right? So the total complexity would be proportional to the number of iterations and the complexity per iteration.
But fixed iterations, when we compare both.
Correct, that's true. Now, you're perfectly right that it's a little subtle, because you at this point we're only focusing on the number of on the total computation per iteration. But then maybe you will require a higher number of iterations to get to the same performance, right? So there are tighter bounds that you can derive that depend on the variance and the number of iterations that is required, and the variance in turn depends on how you choose the batch size, right? So there's a delicate trade-off between the two, no doubt about that. Okay, so now what would stochastic gradient descent for soft SVM look like? Because after all, we have the following nice objective function, which we know is convex. I'll make a small change to the objective function. Instead of having lambda times norm square of W, I'll have lambda by 2 norm square of W. just because I don't want an additional factor of 2 later on, plus 1 by n, I equal to 1 to n times the hinge loss, which is max between 0 and 1 minus yi times the inner product between w and xi. Right. So here's a homework. Compute the subgradient set or subdifferential set for the hinge loss. All right. So at almost everywhere, it's easy to compute the hinge loss because compute the gradient because it's smooth everywhere or it's differentiable everywhere except at 1. Right. The question is so at when the argument is equal to 1, it's not differentiable, and therefore the subdifferential set doesn't contain just one point, but it contains infinitely many points. That's I wanted to compute that. Okay. I'm sorry? The subdifferential set or the subgradient set? Yes. That is the set of all subgradients at all points. Right. So in particular, since I have to choose one subgradient, I can choose the subgradient g of w to be equal to so it's equal to 0 if yi times w transpose xi is strictly greater than 1, and I'll choose it to be equal to minus yixi otherwise. So whenever yi times w transpose xi is strictly greater than 1 or strictly less than 1, this is exactly equal to the gradient. At when yi times w transpose xi is equal to 1, then it's not unique. So that's property number 1. The second property is that this objective function that I have for soft SVM is not just convex, but it also satisfies a stronger condition. It's what is called strongly convex. All right. So if you have any function, so any objective function of the form which is an empirical risk, which is convex, plus some constant, plus a regularization term that is quadratic in the parameters, is going to be strongly convex. So all right. So this is a regularization term, or the L2 So that's another reason for choosing the L2 regularizer. It makes the objective function to be strongly convex. And what do I mean by strongly convex? So there are different equivalent definitions of strongly convex. Remember that if a function is convex, then for any points x1 comma x2, f of x1 is going to be can be written as f of greater than f of x2 plus gradient f of x2, the inner product between gradient f of x2 times x1 minus x2. So in other words, at every point, the function f is always going to be lower bounded by any tangent that for the function, right? So it can always be lower bounded by some kind of a hyperplane, right? That's true for any convex function. For a strongly convex function, it can be lower bounded by not just a hyperplane but a quadratic. So this is plus some mu times norm x1 minus x2 the whole square. So f is the function f is said to be mu strongly convex if f of x1 is greater than or equal to f of x2 plus the inner product. So it's a tangent, not just the tangent, but in fact a quadratic function. For any x1 comma x2. Right? And we're looking at x1 and x2 can be vectors. Right? So at all points of the domain, this must hold. So this part, f of x2 plus the gradient of f of x2 inner product with x1 minus x2 is basically the equation for the tangent plane that passes through x2, right? So just this part would say that f is lower bounded by the tangent for f that passes through the point x2. But here it's saying that it is lower bounded by a quadratic that passes through x2. The advantage of having strongly convex functions is that you can now have better rates of convergence than what you would have using just a standard convex function. All right. I will not specifically look at the exact rates of convergence for strongly convex functions, but for these it turns out that a good choice of the step size or the learning rate so if you have mu strongly convex function, so a slight change, this should be mu by 2. So for a mu strongly convex function, you can choose a good choice of the learning rate is not a constant learning rate or a constant step size. You can choose this to be 1 by mu times t for the tth iteration. So you use a different step size for each iteration, and this will allow you to converge faster. Okay. So let V WT, let me see, be a subgradient for F at WT. Okay, we're assuming that F is mu strongly convex, or let's say lambda strongly convex. F is right, which is what we have for the soft SVM problem. For the soft SVM problem, this objective function is lambda strongly convex. It's a sum of a convex function along with a quadratic. All right, and that's true irrespective of what RS is. All right, what I'm saying is not just specific to soft SVM, but any learning problem where you're trying to minimize the sum of some function along with a strongly convex regularizer or quadratic regularizer. Okay, so if this is the case, then let's look at what the gradient descent step will look like. So we have WT to be equal to WT minus 1 minus 1 by lambda t, because I'm choosing the step size to be equal to 1 by lambda times t, times the subgradient of evaluated at WT minus 1. I'm sorry, yeah, VT minus 1. Okay. Now remember that the function that we are trying to minimize, f of w, is the empirical risk, some empirical risk, plus lambda by 2 norm w square. So VW is equal to the subgradient of RS evaluated at W. Let me call that RW plus lambda times W. Right, where this is the subgradient of RS at the point W. It's any subgradient of RS at the point W. So if I plug this back into the gradient descent step, I get WT to be equal to WT minus 1 minus 1 by lambda t times R WT minus 1 plus lambda times WT minus 1. If I combine the terms that correspond to that have WT minus 1, I get 1 minus 1 by t WT minus 1 minus 1 by lambda t RWT minus 1. I'll write this as T minus 1 by T W T minus 1 minus 1 over lambda T RW T minus 1. Okay, so now I have a rule for WT in terms of WT minus 1 and RWT minus 1. So let me write WT minus 1 in terms of WT minus 2 and RWT minus 2. The same rule holds. Right, so this is T minus 1 by T times WT minus 1, which is T minus 2 by T minus 1 WT minus 2 minus 1 by lambda times T minus 1 R W T minus 2 minus 1 by T 1 by lambda T R W T minus 1. This is equal to T minus 2 by T, because the T minus 1 and T minus 1 cancel, W T minus 2 minus 1 over lambda T R W T minus 1 plus R W T minus 2. Right. Now I can continue this as a recurrence relation. This is T minus 3 by T W T minus 3 minus 1 over lambda T times R W T minus 1 plus R W T minus 2 plus R W T minus 3. This I can go on and on until I get W0, right? Because my initial point is some W0. So this is 0 by T W0 minus 1 over lambda T summation, say j equal to 0 to T minus 1 RWJ, which is just minus 1 over lambda T summation j equal to 0 to T minus 1 RWJ. No, because if you see for WT, this goes on only up to T minus 1, RWT minus 1. All right. Great. So this means, so basically the WT, the tth iterate, is nothing but minus 1 by lambda T times the sum of the subgradients of all of the W, of all of the previous iterates. So when we specialize this to soft SVM, we get a rather simple looking algorithm, because we know that we can choose the following subgradients for uh, for the hinge loss. It's equal to 0 if basically the classifier at the current iterate predicts things correctly, and that too with a positive margin. And you set it equal to minus yi basically you do some kind of course correction otherwise. Right? So the SGD for soft SVM would look something like this. Right? So you initialize you have a separate variable, I'll call it theta t, so let's say theta 0. Let's assume we initialize this with a 0 vector, could be arbitrary, right? And at each step up to t, we'll set wt to be equal to 1 over lambda t times theta t. Okay, and how do you choose theta t, or let's say theta t minus 1? Basically, you choose an I uniformly at random, you choose one data point uniformly at random, and you check. So if yi times w transpose xi is greater than 1, then you do nothing, right? So theta t equal to theta t minus 1. So basically you pick a random data point, you see if this is being classified correctly with positive margin. If that is the case, then everything is good, so you don't change your predictor at all. If not, then you set theta t to be equal to theta t minus 1 plus yixi, right? Because okay. So basically the subgradient is minus yixi for a given data point. So I'm talking about the subgradients of each of these individual loss functions. So subgradient is minus yixi, and here I'm taking wt to be just the average 1 by lambda t times theta t minus 1. So this would be plus yixi. Okay, and that's it. So at the end, output 1 over t sum over 1 to t w t. Okay, so the SGD for solving soft SVM, it's a rather natural procedure. Pick a random data point. If you have classification with reasonable margin, do nothing. If you don't, then you shift by yi times xi. Any questions? Okay. So this algorithm also inherits the convergence properties that stochastic gradient descent could provide us. All right. So far we were mostly worried about or concerned about the rate of convergence of these algorithms, and we saw two algorithms, hard SVM and soft SVM.
Why does the algorithm look very similar to the batch perceptron?
It is essentially very similar to the batch perceptron, because that's what you would do in the perceptron algorithm. You would basically, if it's not being classified correctly, then theta t is theta t minus 1 plus yi xi. It's a little bit of a modification, but yeah, it's pretty related to the perceptron algorithm. But I did not cover the perceptron algorithm in class, so I didn't really give the link between the two. Yi is a scalar, xi is a vector, yes. Yi is either plus 1 or minus 1. Right? So what is the sample complexity of the algorithms that we saw? We've seen hard SVM and soft SVM, and we know that soft SVM, in the case of soft SVM, it's not really an empirical risk minimization with respect to the 0-1 loss. It's regularized empirical risk minimization with respect to the hinge loss. But what we are really interested in is the 0-1 loss. The nice thing is that the hinge loss upper bounds the 0-1 loss. So if we have a bound on the generalization error for the hinge loss, then we also get an upper bound on the generalization error for 0-1 loss. So that's possible to derive some kind of a bound based on the VC dimension. We can also do that exactly for hard SVM. Right? We can get a natural bound on the VC or a bound on the generalization error using or in terms of the VC dimension. Let's maybe quickly recall what that is equal to. Scroll back quite a bit. Just before this. Yeah. So we have the following bound for empirical risk minimization, right? And because hard SVM is actually doing empirical risk minimization, we also have this bound that is given to us. In this case, yeah, so R of H.
In that case, yi plus xi, the weight update, is that really, I mean, usually we have some kind of loss, we have a learning rate. That's how we update weight. Here we did not make some any learning rate.
That's because I chose a specific learning rate, which was 1 by lambda times t.
So then somehow,
Right.
then in that case, does yi xi really come with some related to error?
I'm sorry?
Is the yi into xi?
That basically comes from the gradient or the subgradient.
So that's related to error?
I'm sorry? That's exactly equal to the subgradient, right? Yi times xi if this condition is not satisfied. If yi times w transpose xi is less than 0, then the subgradient is equal to minus yi times xi. Right? It's exactly the gradient descent or stochastic gradient descent, except that the learning rate is now taken care of over here. Remember that theta t is not the quantity that we're interested in. Right? That's not the variable of optimization. It is wt which is the variable of optimization. That's equal to 1 wt minus 1 plus 1 by lambda t minus yixi. Right? It's just sort of a restatement of what is already there. But this particular form essentially looks like what you have in the case of the perceptron algorithm.
But this statement, software C,
Yes.
we are allowing some points to be
Misclassified. Correct. That's true.
For
Yeah.
software learning algorithm only
The original, yeah, it's only for
linear.
it's for in the case where you have a data set that is linearly separable.
So how's this is going to time the software C?
Which this is exactly the soft SVM algorithm, right?
That's
This is SGD for the soft SVM algorithm.
anyway, we are allowing to have some points to be misclassified.
You are allowing certain points to be misclassified, and also in the perceptron algorithm, this would have been the condition would have been this greater than 0 or this less than 0. Right, that's that basically this takes care of that. Okay. Now for the hard SVM, remember that the VC dimension of linear classifiers is d plus 1. Right? So we have the following generalization error bounds for hard SVM. So this means that if we want to get a small epsilon delta error, then it had better be the case that the number of samples is much larger than d. Right? Otherwise, if n is not much larger than d, then this quantity could be fairly large. But that can potentially be a problem because in practice your data sets have very large dimensionality. Okay, so one approach is to take something like dimensionality reduction, but that can potentially cause loss of information, and at the same time it could mean that you're also maybe it's not the separation between points is not enough, and so on and so forth. Right. So is there a way of bypassing all of the dimensionality approaches, or is it possible to derive a generalization error bound that is independent of the dimension altogether? Now without any restrictions it's not possible, but there's a different approach which gives a generalization error purely under some restrictions, and those restrictions are that the data set that you are given has a certain guaranteed margin, that the margin is at least a certain amount. Right? So I'll not prove this result. So suppose that Px is such that data set guarantees what is called a gamma rho separability, which means that W there exists W star for which norm W star equal to 1 and y times w star transpose x plus b is greater than or equal to gamma. So you're guaranteed a margin of at least gamma, and norm of x, maybe I should, is less than or equal to rho with probability 1. So your data generating the ground truth is such that the true classifier, the ground truth classifier, has norm of w equal to 1, and when the norm of w, when it's scaled appropriately, the L2 norm of x of the data point that you observe is guaranteed to be less than or equal to rho with probability 1, and it's going to correctly classify with margin at least gamma. Basically, you don't see any data points that are too close to the actual hyperplane, the ground truth hyperplane. All right? Right? So basically, there is a certain amount of margin that is guaranteed to you, and all of the data points are either going to come from this region or this region, and you are guaranteed that no points are going to come anywhere in this region. Okay. Gamma can be any positive real number, but all of this, the guarantees that we give is with respect to gamma and rho. These are parameters that are given to us. And this particular requirement that the L2 norm of x is less than or equal to rho is also equally important. That is because if you didn't have this requirement, if I only guaranteed this particular, if I only guaranteed that this was true, then I could scale the data set arbitrarily, right, which would also increase the margin. Because if you notice carefully, if for a given x I have a margin, or for a given data set I have this particular margin, if I scale x by a constant factor, then the margin will also increase by roughly the same factor. Right? So I can get an arbitrarily large margin by just scaling up the data set as large as possible. Okay, so that's what I'm not allowing that to happen. The data set completely lies within a ball, and the margin is guaranteed to be at least gamma. Okay.
Shouldn't it be like Wx is less than b, because x is given, x is input.
So x is a random point, right? The random point drawn according to the distribution px, and y is equal to basically w transpose x plus the sign of w transpose x plus b.
So it's very clear, discarding that x.
Which one? No, I'm giving you a data point. This is what the data set guarantees. Okay. If the data set has this property, then whatever I say henceforth is guaranteed to hold. If not, then no. All right. And remember, for this, it has to be linearly separable, not just linearly separable, but with a certain margin guarantee. Okay. So if this is true, then
For a given point, I will free to choose y in this case.
no. So
Tables are not.
let me be more precise. Here, y is, maybe I should have a capital Y here. this is sine of W star transpose X plus P. Okay, this is the ground truth classifier. And in particular, the ground truth classifier has W with unit norm. So again, I'm not allowed to scale W arbitrarily. These are just sort of sanity checks or consistency guarantees. Right, so if this is the case, then the probability that R of Hs or the probability of error of the hard SVM classifier is guaranteed to be less than or equal to square root of 4 rho by gamma the whole square by n plus square root 2 times log 2 by delta divided by n with probability at least 1 minus delta. Okay, so this is, of course, this is under a restrictive condition that your data generating distribution has no points within this margin, but and therefore the probability of error, the upper bound on the probability of error of the hard SVM classifier is now something that scales as 1 over n, but now this quantity depends only on the margin. So this bound continues to hold even when the dimensionality can be arbitrarily large. Even if D is very, very large, I still have this probability of error guarantee. Right. This will be particularly important when we go to kernel SVMs. Because, of course, there's a trade-off. Right? Now I need the fact that I have this margin guarantee. If I don't have the margin guarantee, then this goes for a toss. Along similar lines, we can derive bounds on the sample complexity or the generalization error, even for hard SVM. Right? But this is a little bit different. So if we have, so similarly, for soft SVM, so now I can't really give a margin guarantee because fundamentally the data set is not linearly separable. So therefore it is not possible to derive a bound that works for arbitrary points. Right? But what you can show or what you can guarantee is a bound on the generalization error corresponding to 0-1 loss in terms of the generalization error that can be obtained using the hinge loss. Okay, so if if again the norm of x is guaranteed to be less than or equal to rho with probability 1, then, and you choose, you're only restricting yourself to classifiers for which norm of w is less than or equal to b. Okay, so b and rho are two parameters that you're choosing. And so this right hand side is another restriction that we'll use. Then, in fact, you can say something even further, even without this. So as long as x has norm less than or equal to rho with probability 1, then our the generalization error with respect to the 0-1 loss of the soft SVM classifier is going to be less than or equal to the generalization error of the soft SVM of any hinge loss for any w plus lambda times w square plus 2 rho square by lambda times n. This holds true for all w. So if we choose this lambda to be equal to square root of 2 rho square divided by b square n, then the 0-1 loss of the soft SVM is less than or equal to the min w such that norm w less than or equal to b of the generalization error corresponding to any predictor with norm of w less than or equal to b, but computed for the hinge loss. Remember that this quantity depends on the true data generating distribution. You don't really have this all the time. Plus square root of 8 rho square b square divided by n. The biggest advantage of this is that the generalization error bound on the right does not depend on the dimension. So, I mean, okay, there are these bounds, but at present, are these bounds better than the ones that we get using the VC dimension? Probably not. But here we've made some more restrictive assumptions, and under these restrictive assumptions, this can potentially be better. But the natural question is, do these assumptions hold in practice? All right, because right now, at least for the soft SVM, the assumptions that we made was that the norm of x is less than or equal to rho, and we're looking at classifiers for which the norm of w is less than or equal to b. Okay, is this good enough? I mean, is this a reasonable assumption? If it's a reasonable assumption, then we have a natural bound which could be okay. So there are certain cases where these assumptions could hold. For example, let's take topic modeling. All right, you have a large document, and you want to decide whether the document, you want to design a linear classifier to decide whether the topic of this document is, I don't know, something related to physics or not. It's a binary classification problem. You're given a document, you want to say this is a document that has something to do with science. This is a document that has nothing to do with science. Okay. So how would you go about trying to solve this particular problem? So first, what is a document? The document consists of a sequence of words. All right. So one way of representing this document is, of course, you have to first represent this in Euclidean space somehow. All right. So I have a sequence of words, and I want to represent this in Euclidean space. One potential way is the one-hot representation. All right. So you represent this in terms of a vector of, let's say, zeros and ones, where the component of each vector is equal to 1 if this is equal to the ith word. The ith component is 1 if this is the ith word in your dictionary, and it's equal to 0 otherwise. So the dimension of the one-hot vector is the total number of words that you have in your dictionary. For example, in the English dictionary, maybe you could choose a dictionary size of, like, typically of, let's say, 100,000 or so. All right, that's a reasonable size for a standard English text. So you have, in this particular example, I have d equal to let's say 100,000. Okay. So this, all of these bounds that I have over here would make sense as long as both rho and b, and in particular rho times b, would be much less than d. Okay. Now in this case, what is rho? So remember that rho is the norm of x. All right. Now in practice, maybe the document size is not too large. Just looking at a few words in the document, typically you can make out whether this belongs to science or not. So hopefully you should be able to choose your rho. Like, okay, so rho is the norm of x, right? So in a typical text document, you would not hope to see too many distinct words, right? So for example, if you take a standard text, let's say a page of text, even though the dictionary size is 100,000, the number of distinct words in the text would be, let's say, less than 100 or so. All right, because if you think about it, a lot of words are repeated, articles are repeated, particularly if it's a document that deals with one specific topic, certain terms will be repeated over and over again. So if you sort of create a vector containing all of the distinct words in this particular document, the number of distinct words would be less than 100 or so. So this vector representation of the document would be a vector which has maybe 100 non-zero components, and the rest of them would be equal to 0. And if we are labeling them by zeros and ones, then the norm of this would be something which is definitely less than 100 or so. It's a reasonable, again, we're just doing some back of the envelope calculations over here, right? And now, typically, if you want to design a classifier, hopefully, since you're looking at something restrictive, say science or physics, you should be able to say whether this has something to do with science or physics, by looking at a small number of words. Right? There are certain keywords that if you see these keywords, then you can very easily determine whether this has something to do with science. Right? So potentially you should be able to design a classifier that just looks at a small set of words. You don't know which words to look at, because that's the whole point of designing the predictor or designing the learning algorithm. Right? So hopefully you should be able to choose a predictor that looks at a small set of words, let's say 10 or 20 words. Which 10 or 20 words to choose, that depends on your learning algorithm. But hopefully it should look just at a few words and then decide whether this document has something to do with science or not. Okay. So now even though the dimensionality, because your dictionary is large, because the dimensionality is, let's say, 100,000, the row times B is somewhere between 2,000 or so, which is much less than 100,000. So this means that this prediction that you get, the bound on the generalization, so now you have a bound on the generalization error that depends only on row times B, which is much smaller than the dimensionality. Right? And that's where the advantage comes from. Right? This is not just rho and B, but rho square and B square, if we are using, say, one hot representations. So this is just sort of some intuition to see why these margin-based bounds on the generalization error can potentially outperform VC dimension-based bounds on the generalization error. This is just one sort of toy example, but this will be even more important when we discuss kernel methods, where the fundamental idea is that you take points that belong to some vector space, and these points are not linearly separable, but you try to find a map from this whatever moderate or low dimensional space to a much higher dimensional space where they are potentially linearly separable. When you go to a higher dimensional space, the VC dimension also blows up. If you want to design a linear classifier over a much higher dimensional space, then both the complexity and the VC dimension will now scale up. So there are two issues. One is the VC dimension, the other is complexity. Now this particular approach of margin-based generalization error bounds tell you that at least the VC dimension is not so important. As long as I'm guaranteed a certain margin, everything else goes through. I can achieve small generalization error. How do we lower the computational complexity? That requires a lot more effort. All right, and that's what we'll see in the upcoming classes. Any questions? Okay, so let's stop here.